Luca Formaggia, that is not German speaking. That is not German speaking. Okay, you can see the slides. Block preconditioning, preconditioner for Darcy problem in fractured media. So please, Luca.
Thank you, Stefano. Thank you, everybody, for inviting me at this workshop. This is a joint work with Paolo Antonietti, Anna Scotti, and a master student, Jacopo De Ponte, who did the thesis on the subject. And I start with some motivation of the work. We are working on flow in subsurface flow, so models for subsurface flow with different type of application. And this is an interesting problem, particularly because the subsurface, the rock, is often fractured. And in this slide, I just want to show you, this is just an illustration, that the fractures can have a very strong impact on the underground flow, as you can imagine. Fractures can be either more permeable and thus transport more easily liquids, or can be sometimes impermeable, and in that case, they form a barrier to the flow. And this is the outline of the talk. I will just recall the model we are using for fracture porous media. And unfortunately, I do apologize, but I'm not using here virtual finite elements. I'm using lower order mimetic finite differences, which after all are not so different from low order virtual elements. And I think that some of the results can be extended rather easily to low order virtual elements. I don't have an idea if they can be extended also to higher order ones. Then I will show you some recent results on the spectral analysis of the problem and present a rather classic, in fact, class of approximate block factorization preconditioner, and I show with numerical experimentation how they behave. So fractured porous media, we are concerning Darcy's law in a fractured media. So we have a media that we will normally indicate by omega that is crossed by one fracture or by network of fracture. And this is just to, we're using in this talk, we are just consider basic Darcy law, where the velocity is linked to the permeability, or if you want, this is not really the permeability, it's the permeability divided by the viscosity of the fluid, but anyway, the velocity is somehow proportional to the gradient of pressure. We need to introduce some notation where I use n to indicate normals. I assume that the fracture can be, you can identify two sides of the fracture called plus and minus, and that across the fracture, you can identify jumps and averages, and I'm using quite standard notation from fluxes and averages. We're also assuming that inside the fracture, the permeability tensor can be expressed as the combination of a normal permeability and a tangential permeability. So we may assume that inside the fracture behaves somehow differently in the normal and in the tangential direction. All the illustrations are made, made a mistake. I pressed the wrong button. I do apologize. It happens sometimes to press the wrong button. And now it's taking ages to load. What's going on? Okay. I tried not to press again the wrong button. So I was mentioning I'm using the standard notation for I don't know what's happening. Sorry. It's a problem of my computer. Today things are not going well. It's not responding. I don't know what's going on. Sorry. There was a problem probably in.
We are seeing your screen, but
yes, yes, I'm trying to because I have two screens. Okay, let's do one thing. Sorry, I will convert it to PDF and I show the PDF. I wanted to use something fancy. It's the first time that I try to do this fancy stuff, and unfortunately, it's not working.
The other one.
Yeah, I will just create the PDF and show the PDF. So it's much simpler. After all, I don't have movies, so there is no point in showing the PDF. We need with something else. With the PDF, you are always safe. Okay. So you can extend the thing to a network. So we will consider indeed the network fracture. And indeed, I'm presenting here the notation in with a 2D example, but all the computation are made in 3D. When you consider the network, you have, of course, we define each fracture with a small gamma, and the collection of all fractures is indicated instead with the big gamma, with uppercase gamma. You can also identify, of course, all the intersections and the three tips. That is, we can allow the fractures to be immersed, to have a tip immersed in the domain. Omega gamma indicates omega set minus gamma. So what is left when you put the fractures inside the domain. Again, we assume that for every fracture, we can define a normal, we can define a jump across the fracture, and here are the equations we are using. We are using here a particular formulation where in the bulk, we're using a mixed formulation, while we're using instead a primal formulation inside the fractured networks. This was mainly due for practical reasons, because we already had the code in 3D for the primal formulation. So we join this two formulation, but it can also have some justification. Inside the fracture has got an aperture called L gamma, and inside the fracture now we are using a reduced model where the fracture is indeed represented by a line in 2D and a planar surface in 3D, and we define the pressure in the fracture as average. So the P gamma represents somehow the average of the pressure across the fracture, and Q hat is a possible source term in the fracture. And besides these two equations, we need, of course, to add some coupling conditions, and these are the coupling conditions we are going to use. The first one just says that the jump in the pressure induces a net flux across the fracture, while instead the difference between the average pressure and the pressure in the fracture is responsible to the exchange of flow between the bulk and the fracture. You see that here appear these strange quantities with the hat here and here, and they represent the effective normal permeability and effective tangential permeability, that are the permeabilities in the fracture scale respectively with the inverse of the aperture and with the aperture. So this is the model. I've been presented in many, there is now a classic model. I've been presented many times. This C0 is just a model parameter that has got a fixed value, and we take it as a constant. Of course, we may admit a standard directly nominal condition on the boundary. We assume that on part of the boundary of omega gamma, we have a condition on the pressure, while instead we don't need to assume that for the network. So the network can also be fully immersed. At the tip, we assume zero flow. So there is no exchange of flow through the tip of the fracture. Of course, I didn't quote in the previous slide, at the intersection between fracture, we have to assume something, and we assume classically flux and pressure balance condition. And the functional setting is, after all, rather classical. The only, let's say, different part is the space where we look solution in the bulk that I've called the omega, where we need to, in our formulation, we impose some condition on the jump and on averages. We assume that the jump and averages are can be represented by a L2 function in omega. And in red here I put the extra term that appear due to the coupling. So what you have in black are the standard terms, so there's nothing much to say. But what you have in red here are the extra terms that arise because of the coupling condition. Inside the fracture, the space is just a collection of H1 functions on each gamma kappa, small gamma kappa, where we impose strongly inside the space so that the traces of the pressure matches at the intersection. So we can also define global spaces just by taking the product of two spaces for velocity in the case of the bulk. And sorry, here is just, it's wrong here. This is just that H, okay? This, the space in the fracture is just that H. This is a mistake. If you do the discretization, you get a regularized set of point problem, where again I put in red the terms that arise from the coupling. And you have also this T tilde that is a matrix, a stiffness matrix in the fracture domain, in the fracture network. If rather T is positive semi-definite, so you can easily extend the proof for this class of problem, for this type of formulation, and prove that the problem is well posed. Just assuming that you are imposing pressure on a measurable part of the boundary of omega. We have studied also a little bit the conditioning. The condition, of course, depends both on anisotropy and permeability ratio between fracture and bulks, and also some geometrical characteristic, but that dependence is not very strong. And here you have some papers where you find the proof both for the mixed primal, let's call it formulation, mixed in the bulk and primal in the fracture, and in this paper with Mascotti and Federica Sottocasa, we instead made the proof for the mixed formulation, that was a mixed formulation also in the fractures. So why polygonal meshes? Well, this is really a field where polygonal meshes are very handy, because even if you have let's say standard meshes in the bulk, when you superimpose the fractures, you normally get situations where polygons appears. So these are just showing three examples where even if you start from let's say a standard grid in the bulk, when you superimpose the fracture, so you have some polygons arising. You may do a simplex mesh that is a triangular mesh, but then you want to agglomerate to reduce the number of degrees of freedom that you are going to create in the vicinity of the intersection, or you may have start with just a Cartesian mesh and do some cuts to represent the fractures, or do Voronoi and then followed by again agglomeration to reduce the number of freedom somewhere. In any cases, you get polygons, and so the idea of using polygonal meshes, I think, is very fit for this class of problems. Here is another example of a mesh obtained starting from a very detailed mesh of triangles, where after decimation, you get, of course, also sometimes very regular polygons. So we need methods that are robust on polygonal meshes. Here, as I said, we have just chosen mimetic finite differences. Here, just recall where the degrees of freedom are placed. For the bulk, we have degrees of freedom on the faces for the normal component of the fluxes and at the center for the pressure. Here, don't look at this. This picture was made for the mixed formulation. In this formulation, for the fracture, we only have the pressures that we define at the center of the cell. And the pressure doffs are indeed represent the average values of the pressure in the cell, while for the velocity doffs are the average values of the normal component of the velocity on the face. This is another standard, and of course, you eventually get into standard point formulation after you do discretization with mimetic finite differences. Again, put in red the terms that arise from the coupling with the fracture networks. All the other terms are rather standard. So the coupling appears also in the definition of the mimetic inner product matrix, because you have this term D that I've written here. It is simpler to indicate it in this way, where you have all the jumps and average terms that get inside. For the fracture, we use just a standard finite volume type formulation, and T is the so-called transmissibility matrix. Eventually, you have this saddle point problem that is in fact a double saddle point problem, but it can be rewritten as a standard saddle point problem, as you see here, with the classical matrix called A, B, transpose B and T, and U, omega are the degrees of freedom for the velocity in the bulk, while P hat collects P omega and P gamma that are the degrees of freedom for the pressure in the bulk and in the fracture. And again, you can prove by standard assumption of mesh regularity that I'm not recalling here for the because I'm sure that in another talk that they've been indicated, and the standard one you assume when you deal with the mimetic finite differences. The discrete problem is well posed. But if you go to 3D, it can become rather large and sparse. And that's why we wanted to investigate possible preconditioners for an iterative procedure. And so first we did some study on the spectral properties by starting with some assumption, the families of meshes, that is the volume of cell scales like HD, the area of the faces scales as HD minus 1. D in our case is 3. Here is written in general case, also for the 2P case, but the examples are all in 3D. And that the cardinality of the faces of the polygon is bounded by a constant that does not depend on H. And with that assumption, we also make the assumption that the mesh on the structured network is regular enough so that we have the standard bound for the maximum eigenvalue of the stiffness matrix, where, however, I put this in red to note that you have D minus 3 because the mesh is a one codimensional manifold, so we are losing one, and this is what is causing a result that is slightly different than the classical result, as we will see. The preliminary result we were able to obtain, that we were able to bound the eigenvalues of the mimetic stiffness matrix A by factors that depend on h to the power d for the minimum eigenvalue, and for the maximum eigenvalue d minus 1. These C star and eta are the minimum and upper bound. Well, C star, the C are defined here. I put an asterisk, an uppercase, and suffix asterisk when for the upper bounds, and put an asterisk below for the lower bounds for the various permeabilities, and for this eta that is just an inverse permeability that I've defined in a previous slide. So these quantities depend on the material properties. Okay, the C stars and the K stars and the eta stars. We are also able to bound the singular values of B tilde, again in terms of the size of the grid, and to that purpose we extended work by Luciano Lopez and Vacca on that appeared in 2016. It has to be extended to take into account the presence of the fractured network. And we had also to reach the final result to make a conjecture that we are not so far able to prove, which looks true by using scaling argument, but it's not a rigorous proof that these two L2 norms, these are just two norms, sorry, are not L2 norms. These are two norms of the vectors that represent the degrees of freedom of the pressure and the degrees of freedom of the pressure in the fracture and in the bulk, respectively, scales like H for all the negative eigenvalues of A, and P are indeed the pressure components of the corresponding eigenvectors. We need to make these conjecture that we were not able to prove, but we verified numerically, to finally be able to extend again a classical result, but a better one on the spectral properties of standard point problems, and show that the eigenvalues, the minimum and the maximum eigenvalues of A, indeed you have negative and positive eigenvalues in two intervals. The union of these two intervals is included in the union of these other two intervals that depends on certain parameters and certain constants that depends on the problem coefficients, and H to a certain powers. By that, you get the condition number of A scales like H to the -3. And this was a little surprising because we get a result that looks suboptimal with respect to a classical result for the problem without fractures, let's say the classical Darcy problem. But unfortunately, it is been verified numerically. Here you see a numerical computation of the eigenvalue at scales with respect to H, and particularly when the fracture is very permeable, well, much more permeable than in the bulk, that term, the term that scales badly, is more evident. And here we tried three different grids, hexahedra, tetrahedra, and a grid of polygon. And you see, and here we have the coefficient of the I did a least square fit, and this is coefficient of the line in the log-log plot, and you see that it's practically 3 now. With a polygonal grid, it's more complex to really have an exact estimation of H. So we have a behavior that is not really aligned on -3, but if you use the hexahedral grid where the computation of H is exact, let's say, you really have a -3. This is aligned. I mean, here we have 3 points and they're really aligned on a line. So to conclude, we have also we follow these results, and with the result we see that for sufficiently small h, we have been able to prove that the diagonal part of H of A of the mimetic inner product matrix is spectrally equivalent to the full matrix, and these indeed encouraged us to prove to try to choose some classic approximate block factorization preconditioners, where to the block diagonal, block triagonal, block lower upper, where indeed for the computation of the Schur complement and the computation and the computation of the upper left term, we use the diagonal part of the mimetic mathematics to reduce, of course, the complexity and to have a workable precondition. And we did some numerical tests, first with a single fracture, and we tried, and these examples are all with polyhedral grid, obtained by agglomeration of a tetrahedral grid, but there, we have polyhedra everywhere. Fracture aperture 10⁻². The domain is just a big hexahedra, and the tests are all being made to be fair, to do a fair comparison when the actual relative error is of the order 10⁻⁶. We create a fake solution using random numbers, and we repeated with different random realizations, and we stopped when the actual error is 10⁻⁶, because we wanted to compare the behavior of the different preconditioner in terms of the actual error obtained. And this is the first result we have obtained. We have seen that this n is the number of degrees of freedom and the number of iteration. This is where with relatively small grids, where we and we see that the number of iterations scales very well with the number of DOF, apart with the initial step, but then it's practically constant. And this instead is a cost, is a computational cost in microsecond, but what is not very important for the absolute value is important to see the trend. The LU, of course, is eventually the cheapest one, because despite the fact that it's more expensive per iteration, it gives a substantial decrease of the number of iterations to beat the other choices. Sorry, with the iterative scheme here, I'm comparing GMRES for the diagonal. We also made experiments with MinRes, obtaining results very similar to GMRES, unless when GMRES had to do restart. Here, GMRES didn't need to do restart because the iteration where I put a restart, a quite very high level of restart, so we are not using restart in all of these 3 cases. Here we also compare with the state-of-the-art direct solver, UMFPAC, and we see that already with a relatively small grid, it's not very big, with the LU type of preconditioner, you are faster than UMFPAC. Then we choose to increase the number of degrees of freedom, and the results are consistent. The results are consistent, also increasing the number of degrees of freedom. Here we cannot do the the comparison with UMSPAC because UMSPAC goes out of memory on my PC. But we see again that the growth with the number of freedom is super linear as it was expected, but it's still acceptable. So the increase of computational cost with the number of degrees of freedom grows more or less with an exponent of 1.5. We tried also a more complex situation with a setup more interesting with a real network inside the domain, and also by changing the permeabilities in the fracture, even considering a very high contrast case. For this very high contrast case, the condition number of the matrix is incredibly high, but apparently the preconditioners are very robust, even with respect to the contrast of permeability between bulk and fracture. You see, for instance, the LU preconditioner, the number of iteration is always around 30. I remember that I've always checked that the actual error was of the order, the actual relative error was of the order 10⁻⁶. So in all cases, the final solution is at the same level of accuracy. Here we have also tried MinRes, but MinRes gives more or less the same result than the block diagonal, with of course less memory used. As a final slide, just these are very last experiments we try to do. We try to implement instead the preconditioner proposed by a recent paper by Benzi and Bake on working directly on the double saddle point 4 of the matrix. These preconditioners have the advantage that they require slightly less memory than the corresponding block triangular counterpart that we have seen before, but they behave more or less like the diagonal, because you're doing a stronger approximation of the shoot complement here, because you're not taking into account of a piece of the shoot complement. So it's a compromise. You get more iteration. The timing is more or less the same of the block diagonal, but of course you save memory. You save 30% of memory. So this is the last slide. Sorry if I have taken more time than expected. The objective of this work was to try some classical block preconditioners that are very easy to build using the diagonal part of the mimetic inner product matrix. And we have shown that they look quite robust with respect to H and also to the contrast of the parameters. Of course, for higher dimensional problem, you will have to resort. In this example, the shoot complement matrix was well, the Cholesky factor of the shoot complement matrix were computed. For higher order problem, probably you have to do use an iterative procedure also for solving the shoot complement part. Well, we need to extend it to mixed problem, and but this is a wishing list. Here you have the papers where most of the results that I've shown are present. Thank you. These completes.
Okay. Thank you, Luca.